Hey everybody, this is Larry. Happy Halloween, yay! This is me going over Q4 of the recent weekly bi-weekly contest 38. And that's a mouthful. Hit the like button, hit the subscribe button, join me in Discord. And the problem was number of ways to form a target string given a dictionary. So this one was a little bit tricky to read. I think just about there's a lot of reading definitions here, and I think I got a little confused reading this. But basically, when I look at these problems, the first thing I do, or one of the first things I do, I think I took a little bit of time here, is just look at the constraints. And there are at least 1,000 words, or at most 1,000 words. Each word is 1,000 characters. You have a target that's also has 1,000 characters. So the thing that I try to look for is kind of a way to, so my immediate job is dynamic programming, especially when it comes to counting things, number of ways, and you have a big module. And of course, first thing I did was I put mod everywhere, but because I keep on making that mistakes from time to time. But so after that, the first thing I do for dynamic programming is noticing that, or try to figure out some kind of property in which in this case it is what I call a prefix or suffix, depending on which direction you go. It's the same idea. Dynamic programming, and what I mean by that is that the current state only depend on the suffix or the prefix. I mean, because you could go in that direction. In this case, I actually did it with the prefix. No, I did it with the suffix. So you only care about the suffix, right? And what I mean by that is that there's no interaction between the decisions that you're making. Meaning that if you change how you chose, your decisions later cannot affect how you change the decision now, right? So that's kind of how I think about these dynamic programming problems. And for this one, the key thing to note is that the order of the words don't matter, meaning that these are just like a bag of characters, right? And the way that I thought about it is because it doesn't matter, you could compress them into one super word. That's my thought during the contest, where for example, in this case, instead of going for each word one at a time, because then it could be like n cube or something silly, right? If you do it, so actually, let me talk about the naive way of doing it first. If I have to do a naive way, I'll be like, okay, the first character, the naive dynamic programming. So there's some prerequisite around dynamic programming. So if you're a little bit weak about it, definitely practice that up and then maybe come back afterwards. But the way that I construct my state is that, okay, you have the number of characters you still need to solve on the target, and the number of characters that you can still use from words, right? Because that's just how they define the problem in the problem. Because once you use a character in a word, you cannot use any characters before it, and so forth. So that if you use an index, you cannot use anything to the left of it, right? That's literally what the problem statement said. So then the naive way to think about it is, okay, one naive way is that, okay, we need an A, right? So let's look at every word's first character and then do a recursion on that, right? Okay, we found A here, yay! So then we do a recursion on that. And that's kind of how this looks like. The first four of these things, that's basically what's going on. And then you get, okay, and in classic dynamic program kind of way, another way to do it is just, in this case, you cannot skip any character in target, but you can skip characters in words, right? So then we go to the second character and we go, okay, so we're still looking for an A. Let's look for an A in words. So C, okay, that's not good, so we can't do that. B, no good. Oh, look, it's an A, that's good. So then that's basically what this is here, right? So basically, very brute forcey recursion, and that's how we would solve this problem. But because words can be 1,000, every time you go through this list, it's going to be 1,000 times. And I don't have great visualization tools here, but as we talk about, the states is the number of characters in target and the number of characters in one word character. So that's 1,000 squares. We look at this, and if we do a loop around each word, which will make it 1,000 cube, which is too slow, obviously, for this problem. Even with memorization, even with dynamic programming, it's gonna be too slow. So how would you fix this, right? Well, I think looking at this example is a little bit better, because now, if you look at it naively again, one by one, we go, okay, we need an A in the target. Maybe this is easier to read. We need an A in the target. So we go, okay, we can, we look at one word, go, okay, let's do a recursion based on this A. This is a B, we cannot do that. Oh, this is an A, so let's do recursion based on this A again. And then B, we cannot do that, right? So if you just kind of go through that mental, you go, okay, actually, that's just, if you kind of try to compress it, that just means that in the first characters, there are 2 ways to use an A to match this A, right? Huh. So then my thought process was, is there a way to compress that, right? Well, the answer is just by using a lookup table. And that's basically what I did here. I have a lookup table. This is a count for each index and for each character and that index. And basically the idea is that this lookup table is a compression, a crazy super words, if you will, where the first character has 2 A's and 2 B's. So basically you literally just look at them. If you look at this word or this word list, and it's easier to visualize once you kind of compress it like this. That if you look at just the first character, there's 2 A's and 2 B's, right? In the second character, 2 B's and 2 A's. Well, in this case, actually, it's always 2 A's and 2 B's. But you get my point. You get my drift. So basically, that's what this code does. And once you have that, then now it becomes easier, right? Because that means that at each state, at A, we can either use one character from word. Like we could either use one column from words, or we don't, right? And those are the 2 decisions we get to make in this dynamic programming. And that's pretty much the basis for how we solve this problem. We pre-calculate this, we compress the counts for each character at each index, and then our recursion is just poorly named, but index from the words and then the index on the target. If we are able to get to the end of the target word, then our result is 1. If we ran out of characters on the word list in the dictionary, then there's no way to do it because we ran out of characters. And then these are just the 2 ways, and I do make sure we do some mod math, but basically we go, this goes, we skip this character in the dictionary because we can, and here, and you can actually add an if statement, because obviously this is going to be, you go to 0 if this gets chopped up a little bit. There you go. Because this is obviously going to be, you go to 0 if there's no characters there, but it doesn't affect the running time. Maybe it affects the running time, but not the big O complexity. And this is just, okay, we can, the number of ways. So in another phrasing is that, if the first character in target is A, this is just the number of A's in this in this column, and then we just it's like a classic matching thing where we match and then we move 1 to the right. So that's basically how this problem works. That's how this solution goes. And what is the complexity of this, right? Well, let's see. Index could be from 0 to, in this case I named it NW, but let's just say 1,000. And target index can go from 0 to NT, which is also 1,000. And if we look through this, we don't have any for loops, we don't do any iteration work, so this is just going to be O of 1. So for each call to this function, it does all of one work. We have at most 1,000 times 1,000, or maybe n sub w times n sub t equals to this function. So total work is equal to O of n times O of n sub w times n sub t. And that's pretty much the time complexity. And the space complexity is going to be n, also n sub w times n sub t is really hard to say, actually, really fast. So yeah, that's all I have for this problem. You can actually upsolve this if you like by rolling this to a bottoms-up dynamic programming. And once you do that, you can there's actually, for this problem, you can actually reduce the space to O of n sub w, or maybe O sub n sub t, one of them, but more, you could reduce one dimension in the space. And you could, maybe I'll put a link below on my tutorial on how to do that, or explanation how to do that if you're interested. But yeah, and this is also O sub n w times the number of words, which is 1,000 square again. But yeah, that's all I have for this problem. Let me know what you think. Here's a little bit smaller so you can see everything. It's about 30 lines of code. Yeah, so let me know what you think about this. You can watch me solve it live during the contest now. Oh, I misread this. Okay. But slow, but I got this. Whew. Okay. Yeah, thanks for watching. Thanks for hanging out. Let me know what you think about this explanation. Doing a little bit live, so yeah, hit the like button, hit the subscribe button, join me on Discord, and I will see y'all next problem. Bye bye.